Hello everybody. This video we are going to be looking at engine schematics and efficiency of engines. So the last video we went through this picture, and this picture has just a lot in it. There's nowhere I can even put my bubble and not be in the way some. So how do we summarize this in a way that's useful, gets the big picture in one clear visual where I don't have to be overwhelmed by all of the nitty gritty detail of this work? And then how do I look at this engine and say, is this engine even any good? So those are the two questions we're going to answer. So let's look first. Let's consider a different type of engine, both because I want you to think about this as an engine, but also because I think it's more helpful in this conversation. So this is a power plant, maybe a coal-powered power plant where we're burning up coal and releasing the internal energy from that coal. Or maybe it's a nuclear power plant and we're releasing the energy from the nuclear bonds and uranium. Either way, they run on this same process with some sort of fuel burning or running through their process. And so let's look at this schematic here. This is a steam power plant. We've got some substance that's doing the working inside of an internal combustion engine, a diesel engine. That's going to be the air fuel mixture. Inside of a steam plant like this, it's going to be water. And we are adding energy into the system through a heating process. That energy is coming from the fuel. It's already stored in the chemical bonds of the coal or the nuclear bonds of the uranium, and now we are releasing that energy and sending it into our system through a heating process. And so that's where the energy is coming from initially, is the bonds inside of the coal. The energy transfers into our working substance through heating. Whoop, back up. All right, we've got a steam line here, and then that steam is doing work on the environment. There is a working process that happens. Typically, this steam is turning some sort of a turbine, which is windmill-like, is the best way to think about it. And it's that turning process which generates electricity. We learned earlier this year then that turning motion, if you turn a magnet around a coil of wires, then that change in flux of magnetic flux through that coil is going to generate electricity, and then we can send that electricity out through power lines. So that's the gist of how these steam plants work, but that's not it. It is required through the second law of thermodynamics that we have a cool reservoir where the excess heating that's there goes back down to a lower temperature. So the working substance heats to cool the water. And this causes the working substance to condense. So we have this cooling reservoir here, and we repeat that cycle. So heating reservoir, some hot reservoir, the fuel. We've got the working substance, and we've got a cold reservoir. So three things to keep track of: hot reservoir, the coals; the working substance, which is the water here or the gas inside of an internal combustion engine; and we have the cold reservoir. Substance is being impacted by hot and cold reservoirs. All right, schematic of this, a more abstract but easier to look at and draw a picture. Hot reservoir, this is our coals in the picture before. This is what we're burning. Cold reservoir, that's what's doing the condensing over here. And then we've got the engine is the substance. This is the water. So three things: coals, the thing doing the condensing, and the substance here. And heating is flowing from the hot reservoir into our substance, and then heating is flowing from the substance into our cold reservoir as well. This number up here is going to be smaller than this number up here because some of that energy that went through this engine is leaving through a working process. So that's our schematic. Heating enters our system, and then energy leaves the system through some combination of working and then heating the cold reservoir. Here's our example problem. So where did that fit in? The heating that was done to our substance, that happened from A to B and from D to A, if you go back and look at that picture. And if you add up those two heating sources, that's going to be 5.25 kilojoules that we added into our system total through a heating process. We look at the heating that left our system. Well, that happened during B to C and C to D. And if you add up those two, you end up with a loss of 4.25 kilojoules of energy through heating. And if you go through and you look at the net amount of working that was done, you add up all of the working between each process, some of those were 0, you ended up with a negative 1 kilojoules. We sent 1 kilojoule of energy out into the world. And that is the summary of our process. I think this is nicer to look at than the picture we had before, but I think we need to use the picture we had before first before summarizing. And now the last thing to note here is that if we ignore the signs, you take your difference in heating, 5.25 minus 4.25, you end up with 1, ignoring all the signs there. In other words, whatever energy enters leaves through those two processes. Or we're trying to steal as much of this heating as we can for working, but we can't do that perfectly. Take a second, reflect on what I just said, think about this a bit more. I'll say one more time, energy in, 2 energies out, those are going to be the same number because energy is conserved. We want the energy out through working to be as much as possible. All right, efficiency. It's a measure of how good your engine is the idea. And we're going to look at answering this question. Of all of the heating that flowed into our system, what percentage of it was actually useful? What became work that we could do something with? So that's the question. Of all the energy that entered our system, how much of it became useful work? As an equation, this definition is shown below. The efficiency, lowercase e here, is the working that the substance does on the environment, which is the useful work, divided by the heating that the hot reservoir, the coals, added into our substance, the water. So that's our efficiency. And with this definition, we're ignoring any minus signs. We're just looking for a percentage. So the efficiency of our engine, if you back up to the schematic on the last slide, it was 1 kilojoules of useful work, but we added in 5.25 kilojoules of heating to make that happen. So it was only 19% efficient. In other words, 81% of the energy that went into our system just left through cooling. We didn't get to move anything with it, which is what our goal was. So 19% efficient, not excellent, not very good. But right now I want to give you some sort of a reference for what is a good number. So first, the total useful work done on the system has the same value as the difference in the input and output heating, which is what he said earlier. So it's equivalent to compute heating by looking at how much heating did we add into the system, subtract off how much left, that whatever leftover there is, whatever change there is, well, that's got to be the working. So same idea, and again, plug in positive values for each of those 3 variables. Now, the physicist Carnot, he showed that there is a theoretical maximum possible efficiency for a given hot reservoir at a temperature TH and cold reservoir TC. So this is not the temperature of the water, the working substance. This is the temperature of the coals, the hot reservoir, and of that cold reservoir where the water was getting condensed. So we're not going to prove this here. It's a little bit beyond the scope of this course, but this is the maximum possible efficiency given a heat driver and a cold driver. You'll notice that in order to get a perfectly efficient, 100% efficient system, that this cold reservoir would have to go all the way down to 0 Kelvin, which cannot physically happen. So we could only get something less than perfectly efficient. We're never going to get a 100% efficient engine. For many cars, this is where you're going to get a sense of scale. Efficiency is around 30 to 40%. If you're pushing that 40% efficiency, that's considered a very efficient and a very good car. It is just not physically possible to do much better than that due to this theoretical limit. There's a limit based on the temperature differences between your hot and cold reservoirs. So that's the end of this. Main picture was this idea of efficiency, and backing up some more. this summary schematic of an engine. So I hope this was helpful. If you have any questions, please let me know, and I'm always happy to help. I will talk to you later. I'm signing off.